Right, this is an example here where we have a rocket ship, believe it or not, this is a rocket ship here, traveling at 50 meters per second out in space. It's currently traveling at a constant velocity. We are going to start the problem when this rocket ship throws on some reverse boosters, so I think those reverse boosters would set out a spray that way, something like that. I'm quite the artist here. And it's going to slow down, and it's going to slow down at a rate of 2 meters per second squared. I should point out I kind of just tossed in this negative. The reason for me tossing in the negative is because if it's moving in the positive direction and it's going to slow down, it needs to be losing speed, so losing 2 meters per second every second. So it's going to slow down at that rate, and we want to see what happens after it's gone 100 meters. So I want to know basically mostly how much time it takes to do that, but once we find the time we can also find some other information. So we're gonna work on finding time. So I'd just like to point out that this is kind of what would be shown in the textbook, this kind of information. So what I'd like you to do here is take a second to try starting the problem, particularly by drawing some graphs. And so it'd be good if you paused the video at this point and tried to draw some graphs, and then I'm going to draw them here in a second. So hopefully now you have taken a look at your graphs. So I particularly like velocity time graphs because they tend to be kind of straightforward. And so I'm going to take a look at that first. So I'm going to draw velocity versus time. And we know that our initial velocity is 50 meters per second. And kind of the indication here is that we're starting the problem the instant these boosters come on. So it's going to start slowing down at a rate, which means that we have a slope of -2 meters per second squared, because the slope of our velocity graph is acceleration. And it's going to do that for some unknown time amount that we don't know, hence unknown. Now, we could do something where we say, hey, we know the area under this graph has to equal 100 meters. And we certainly could kind of set up a formula for that. And that would absolutely work. That is not the approach that I'm going to take right now. What I'm going to do is start looking at our equations that we have. We know that for this graph, our final velocity equals our initial velocity plus acceleration times time. So I'm going to plug in what we know and see if that helps us at all. Our final velocity, which we don't know, is our initial velocity, and then our acceleration is -2 meters per second squared, and we don't know how much time. So the problem is right now is we don't know the final velocity, we also don't know the time. This isn't going to help very much. So now, if you haven't yet, it would be a good idea to try drawing a position versus time graph for this situation. So now I'm going to draw a position versus time graph. And since we're starting out at 50 meters per second, that means we have to start out with a steep slope. Particularly, the slope at the very beginning would have to be 50 meters per second, because the slope of our position graph has to equal velocity at that instant. But then that slope is going to decrease as time goes on. And so we don't know if it gets to 0. We basically are looking for this time right here, sometime after we've gone to the 100-meter mark. Now I started at 0 here. I didn't have to start at 0. I could have started at 50 and gone to the 150 mark, as long as this total displacement is 100 meters. So now we try to set up our equation that represents position versus time graphs for constant acceleration. I know that I have half my acceleration times time squared plus my initial velocity times time. Now if I wanted to know the final position x, I would add the initial position x naught here, but instead I'm subtracting that so that I just have displacement overall. So now I'm going to plug in the numbers that I know here and see what we can do. I actually know that my displacement has to be 100 meters. I know that my acceleration is -2, and I know that my initial velocity is 50. So at this point we have an equation that simplifies to 100 equals -t squared, 1/2 times -2 is -1, plus 50t. Now what that means is that we have a quadratic equation where we need to solve for t. Okay? Now I'm going to back up, because if we're, back in CIS physics, one of the things we want to do is we want to be able to solve things algebraically first. So I'm going to back up to here. Since we can't just solve this particular problem, we're going to look at it from this perspective, and I'm going to go to the next page to look at that and solve it. So what we've got is this equation. Change in x equals 1/2 at squared plus v0 t. Now, we know these different values. What I'm going to do is get this in the standard form of a quadratic equation. So I'm going to subtract change in x from both sides. And by doing that, I end up with 0 equals 1/2 at squared plus v naught t minus change in x. Where now, this is the a term of my quadratic, this is the b term, and this is the c term. So now I'm going to go and look at my quadratic formula. If you recall, x is equal to negative b plus or minus the square root b squared minus 4ac all over 2a, which, by the way, you do not have to memorize. Okay, you don't have to memorize any of these formulas, actually. But in this case, time is our x value. So really what we're saying is that the time will equal this particular equation. So I'm going to go through and plug in these different things. So I'm going to have time equals negative b. Well, that's negative v naught plus or minus the square root of b squared, that's v naught squared, minus 4 times a, which is 1/2 a, times c, which is negative change in x, all over 2 times a, which is 1/2 a. So, oh, sorry, yes, 2a, 1/2 a. So then I'm going to just simplify this. T equals negative v naught plus or minus the square root of v naught squared. So here we have a minus and a minus, that's going to be a plus. We have 4 times 1/2, that's 2. So 2a change in x all over a. So keep in mind this a is acceleration. This is our initial velocity. These are all values that we know. Now at this point we can numerically solve this because this is not simplifiable in any way, shape, or form from here. So what we do now is we plug in numbers. Our final time is going to be our initial velocity plus or minus our initial velocity squared plus 2 times our acceleration, which is negative 2 if I recall, and our displacement was 100 meters, all over our acceleration, which is negative 2, which simplifies to negative 50 plus or minus 50 squared is 2,500. This, I believe, works out to be negative 400. So 2,500 minus 400 is 2,100 divided by negative 2. Now, what I'm going to do is, to finish solving this, I'm going to break this up into the plus or minus. I'm also going to take that square root. So it turns out the square root of 2,100 is 40, nope, I don't have it on here. I'm actually plugging it into my calculator, believe it or not. 45.8. And so that means time is negative 50, and I'll go with the plus first, plus 45.8 divided by negative 2. And two solutions to quadratics typically, negative 50 minus 45.8 all over negative 2. Okay? So then it turns out this answer here, negative 50 plus 45.8 divided by negative 2, I believe ends up being positive 2.1 seconds. It's because when you add this you get a negative, and then you divide by a negative and you get a positive. Same thing here. We end up with negative, let's see, negative 90, obviously 95.8, dividing that by 2, negative 2 really, and we get t equals 47.9 seconds. Okay, so we have two answers, so which one's the right one? Kind of intuition tells you, I hope, that the smallest one is the right one, but we're going to look at the graph actually to figure this out. If you go back to our position versus time graph, I've really only drawn half of a quadratic here. This quadratic, which I'm going to sketch once again down here, which I believe you can see, actually comes back down again. And here's the idea. We hit that 100 meter mark at 2.1 seconds. If those backwards boosters kept firing, the rocket would stop at some point and it would have a velocity of 0 at that instant for a moment because the slope is horizontal. And then if they kept firing, it would actually start accelerating, speeding up rather, back the other direction, just like a car on a ramp. And so, you probably actually can't see that now that I think about it, that I'm pointing to, but so these boosters would keep firing, and it would actually push it backwards, just like the ramp. And so, that means we once again hit that 100 meter mark. It turns out we hit that 100 meter mark at 47.9 seconds. And that is why there are two solutions. This is the one that we really want. This is one that's still a sensical, but it's not really actually the implied question that was asked.